in order to define our creation and annihilation operators, it's good to have a convenient notation for elements in the bosonic Fock space. Elements in the bosonic Fock space are given by symmetrizing general elements, and of course we should, instead of writing this element as a symmetrized sum, we should just use a compact notation, and here's the one which I'm going to use. So namely, let us say we have elements x1 up to xn in the Hilbert space, and then I'm taking their tensor product, so that would be the elements in H tensor n, but we only want symmetrized versions, and this I denote, just in order to distinguish it from the tensor, I denote with a small circle between them. So I write x1 circle x2 circle x3 circle, so dot xn. And with this I mean I'm taking the tensor product of them and symmetrize them, but I'm also putting there some n factorials, because in my operator p I have an n factorial, and I'm getting rid of this, but only, let's say, half, because I'm taking the square root here. So I mean, in all the formulas which I have for creation and annihilation, at some points square root of n guys will show up, and it's just at some point one has to put them into the definition, and one can change the definitions a little bit and move around the square roots of n, but one cannot, they are just there. So, and I'm using this definition because I think the creation and annihilation operators have then a nice description. Okay, so I'm taking Pn, so I'm symmetrizing x1 tensor x2 tensor up to xn. I'm symmetrizing this, but then I also multiply it with the square root of n, and so this is an element. Of course, it's in the image of Pn, so this is an element in the n's tensor power, the symmetric part of it, of n. And I mean, those guys, linear combinations of those guys and limits of them, they will generate this thing here. So I essentially have to define my operators on elements like this. And before we really do this, maybe a few remarks on what we really have here. So first of all, of course, if I exchanging here the axis, nothing will change, because this is clear by definition, because the symmetrization of x1 up to xn is of course the same as if I have here a different permutation of the axis. So this is clear that if I permute the indices here, x of sigma 1 circle x of sigma n, this element is the same as x1 circle x2 and so on circle xn for any permutation of the n indices. Good. But maybe a more interesting question is, what actually is a nice orthonormal basis in my symmetric tensor power space? I mean, we have seen if I just look on the tensor power, then I can take just an orthonormal basis in H and take any tensor products of them, and they together will form an orthonormal basis of H to the n. Now, of course, we only go to the symmetrized version, and this means, in principle, we should take this version here, the symmetrization of the orthonormal basis which we have here before, but of course now not all of them will be different, because if I take, for example, if I take E1 circle E2, this of course is the same as E2 circle E1. So this means because in the symmetric tensor space those guys commute, what I really need are only this kind of tensor products of the orthonormal basis in H, where actually I order the indices. Because whenever they are not in the increasing order, I can exchange it because everything commutes. So this means what I should take is just the tensor product of the E's, but only for index tuples which are in a increasing order. So this is the second part here. So if the EI, let's say E is an index set capital I, which is either 1 up to D, or it can just be the natural numbers if my Hilbert space is infinite dimensional. So if this is an orthonormal basis of the base Hilbert space H, so if this is an orthonormal basis of H, then I can get a basis of the symmetric tensor power by looking on all the tensors of E, this index I1, E I2, and so on, up to EIN. But now I should not take any choices of the E's independent from each other, but only the ones which are increasing. And of course, I mean, some of them might be the same, but it should be an increasing sequence. So I require that, of course, all the I's here are in this index set I here, but otherwise I1 should be less or equal I2, less or equal I3, and so on, up to less or equal to IN. Because if I have a different order here, then I can just commute it into an order like this. And so now the point is, this gives me a basis of my symmetric tensor power, and different elements here are still orthogonal, but they are actually not normalized to 1. So that's maybe that's a disadvantage of this notation. So that I'm getting a basis which is not an orthonormal basis, it's only an orthogonal basis. But I mean, for most things this is still good enough, but the advantage is that in this language, in this notation, the creation and annihilation operators, they don't need they don't need square roots of n numbers in front of them, but they are somehow hidden here. Okay, so the point is here. So this is a basis, a Hilbert space basis of the symmetric part of H to the tensor power n, and so this is orthogonal. So different elements there are orthogonal to each other, but it's not orthonormal. Yeah, and maybe we should check this. So let us just see what is the inner product between two such guys. Also just to make sure that we understand what I'm really defining here. So let me take two such elements here. So the one index tuple I call I and the other I call J. So I want to see what is the inner product between E, I1, circ, and so on, circ E to the IN, inner product with another guy of this form, which I write the indices as J1 up to Jn. So this here is an increasing sequence of elements from I, and this is also an increasing sequence of elements from I. And now let me just put in a definition. I mean, those guys are just symmetrized versions of the corresponding tensors. And let me write this. And I also have the square root of the n factorial. So I have it from here and from here. So I just get an n factorial in front of the whole thing. And then I just have to plug in the Pn. And the Pn is doing what? The Pn was defined by 1 over n factorial, taking the sum over the permutation group, so over sigmas, and then I have to act with the permutation sigma on the order which I have here. So I take those guys here, but now I have to permute them with sigma. So what I get here is now E of I sigma 1 tensor and so on up to tensor E of I sigma n. So that's this guy here, and here I'm doing the same. So I'm applying Pn, and Pn is again, it's 1 over n factorial, summing over the permutation group. Let's say I'm summing over pi, and then I have to apply the u pi on the vector which on the tensor which I have there, which just commutes the indices according to pi. So here I get e of j pi 1 tensor e of I pi n. Yeah, and now you see this n factorial cancels one of this 1 over n factorial, so I'm left with 1 over n factorial, 1 over n factorial, and I'm left with the sum over the two elements from the permutation group. So I'm still summing over sigma and pi in the permutation group. And now I have the inner product between this and this for each fixed choice of sigma and pi. And, and in the tensor product of Hilbert spaces, the inner product is just taking the product of the inner products between the corresponding factors. First with first times second with second, third with third, and so on. So I have to take the inner product of this with this, the second here with the second here, times and so on with this with this. So okay, let me write it down. So this is the inner product of e to the I sigma 1 inner product with the first term here, which is e of j pi 1, and then multiplying all those, and the last term is the inner product of the last factor here, which is e I sigma n inner product. Maybe here I'm putting brackets. So okay, inner product with e, and here I have a j, j of pi n. Yeah, and now of course the e's, so these are now inner products in the base Hilbert space H, and there the e's are an orthonormal basis. So if I take the inner product between two of them, their indices better should be the same, otherwise it is equal to 0. So this means if I want to get here something which is not equal to 0, I need that that this index here is the same as the index here. Yeah, and this means I must find a permutation of the second indices which matches the first indices. Okay, so if the I indices are somehow as a set, if they are different, if the I indices are different from the j indices, then this is 0, because at least one of those guys is equal to 0. So what I get here is, first of all, 0. So I mean I have orthogonality. I have the orthogonality which I claimed. So this is 0 if this tuple I1 up to In is not the same as the tuple J1 up to Jn. Yeah, because I mean the i's are increasing, the j's are increasing, and here I mean I'm still I apply sigmas. Yeah, but I have to guarantee that if I'm applying a permutation sigma here and a permutation pi here, that I get a matching between those guys. And this means I mean they really must be the same, otherwise I cannot find a matching. Yeah, but if they are the same, then here I get something which is not necessarily 1, but it depends actually on the structure of the indices here. So what I get here, maybe I just write it down. So this is, and again you see I have here sigma and here pi. So this means I do a permutation here, and then I do a permutation here, and then I have to match. But of course this is the same as if I just write it here in a original order, and here I'm applying let's say a sigma to the -1 pi. Okay, so this means the product which I get here is if I'm fixing the sigma and I'm summing over all the other pi, is always the same, which means the sum over sigma, let's say, is cancelled by this 1 over n factorial, and I'm left then just with the sum over the other guys. So what I get here is actually summing over, let me call it tau in Sn, of E of I1, and this must match one of the j indices, but the j indices are now must be the same as the I indices. So here I also have the I, so it's the I of tau 1 times, and so on, E of In, which has to be matched with E of I tau n. Yeah. So if the I indices are the same, I1 up to In is the same as J1 up to Jn. Yeah, okay, and the actual value of this now really depends on I1 up to In, because they can be all different, or the other extreme case, they can be all the same, or some of them are different and some of them are the same, and then I get different results. So for example, let me look on the inner product where they are all different. So for example, I would then have E1, E2, E3, and so on, let's say up to En. I'm just taking them in increasing order, but none of them is the same. So I really make here, take a different one, and I take the inner product of this with itself, E2, E3, and so on. Yeah, and then this formula here tells me I should take permutations of this and then match. So I match the first with the first, the second with the second, but I can also do a permutation here. Yeah, but you see, I mean, I must match the E1 with the E1, because it cannot be matched with the other ones. So in this sum, only the identity permutation here gives me contribution, and this gives me then, of course, just the inner product of E1 with E1 times the inner product of E2 with E2, and so on. So this is just equal to 1. So in this situation, when all the i's here are really different, then the norm is 1. But if some of them are the same, then it will change. And for example, the other extreme is where all of them are the same. This can also happen. So if I have E1, 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 and I take the inner product of this with E1, E1, and so on. So this is a valid element in my symmetrized version of the nth power, and now I should take here the sum over all tau, so I can do all permutations here, but you see, any permutation will give the same, and after the permutation, I have to match this with this, this with this, and so on, but each mapping gives me the contribution 1, because I mean this E1 can be matched with any of them here, the inner product is always 1. So in this case, for each tau, I will get here the contribution 1, and so I get it altogether n factorial times. So this inner product here is n factorial. Yeah, good. And of course, I mean, if I don't like this, I could normalize those vectors by 1 over the square root of n factorial. But then, of course, I would also have to change my definition of these vectors, and later in the definition of creation and annihilation operators, I would have square roots of n would show up. So I mean, here I have a factor somewhere, but it's hidden in the normalization of those guys. Yeah, and maybe if you're looking back, when I talked about the one-dimensional CCR in the language of A and A star, then I mean, I created out of the vacuum, I created something which I called En. So in the language, I mean, there. So in 7.4, I mean, we looked on guys where I took the A star, the nth power, acting with this on omega, and then I got something which I denoted by En. And those ENs, those are nice operators if I use them for defining what is the action of the creation and what is the action of the annihilation operators, but they were also not normalized. And those En, this what is here, what was there called En, this is now, this would be this guy. And there I said, instead you can consider Fn, which you redefine, so it would be 1 over n factorial of En, and then you have then you have an orthonormal basis, but yeah, some other formulas won't look so nice. Huh? So maybe I stay with those guys, define migration and annihilation operators in terms of those, but you should have in the back of your mind that yeah, if you take a basis in H and you write down what is the canonical basis in the symmetric version of H to the n, this is not orthonormal, but you will have some lengths there which you see are not uniform. Huh? It's not only, it depends not only on length, it's not a factor which is the same for all of them, because otherwise I could just divide it out. But it's really something which depends on how many of the indices here are the same and how many are different. Yeah, good. Okay, so as I said, this has an advantage for defining gradation and annihilation, and so now I really should do this.